Hello everyone, welcome to the second lecture in this series of nanotechnology. This is our second topic. Previous lecture is the introduction to nanotechnology, and this lecture focused on surface to volume ratio, the power of small. I welcome you all, myself Dr. Babu Batula, Professor and Dean, School of Sciences and Humanities, SR University, Warangal. In this lecture series, we will talk about introduction to surface to volume ratio. What is surface to volume ratio? In our previous class, we have discussed about introduction to nanoscience, nanomaterials, and nanotechnology. So we have discussed two things which are crucial for the significant properties of materials at nanoscale range. Two reasons. So we discussed about two reasons. So the first one is surface to volume ratio, and the second one is quantum confinement, right? So in this lecture, we will discuss about surface to volume ratio. What is surface to volume ratio? How it increases or decreases? How it influence the properties, be it mechanical properties, chemical properties, physical properties, catalytic properties, so whatever. So how it is significant, how it plays a major role in deciding the properties of nanomaterials, right? Okay. So if you see this one, the picture here, you can see the picture here. So it is a bulk material. It is a bulk. It is a bulk material. So this is the bulk material, right? This is the bulk material. So we have discussed about two methods to prepare nanomaterials. One is top-down approach. Second one is bottom-up approach. In top-down approach, what we will do? So usually we take a bulk material and we divide it into pieces. Okay, so as the pieces increases, so what happened, the surface area will increase. Okay, the surface area will increase. So that is top down approach. So here we are taking a bulk material and it is make into multiple pieces. Okay, so what happened when we divide a bulk material into multiple pieces is, here you can see, the surface to volume ratio is a fundamental geometric property describing how much surface area is available relative to the volume of an object. Okay, relative to the volume of an object. For example, if you take a bulk material, so the available surface area, the available total surface area is very less. Okay, the available total surface area is very less. But if you consider the same material in different pieces, in multiple pieces, so we can observe that there are many faces. So there much more surface area is available to interact. Okay, so there is so much surface area to expose. Okay, so that the surface energy will be very high. Okay, so in simple words, the surface to volume ratio is a fundamental property related to surface area. So and how can we describe it? How much surface area is available relative to the volume of an object. Okay, so that is important. So this ratio plays a critical role in determining the physical and chemical behaviors of materials, especially at nanoscale. So we already discussed about that. So once the surface area increased, so the majority of the atoms so will come to the surface area and they are free to interact. They are free to interact with other particles. So that's why, so surface area is nothing but the availability of atoms at the surface. So in bulk materials, so the available surface area is very less. So most of the atoms are inside the bulk material, so which cannot participate in any reaction. Only the atoms, only the molecules at the surface are only interact or participate in any chemical reaction. So that's why surface area is very essential. So if surface area is less, that means in bulk stage, so less number of atoms are exposed or less number of atoms are available to participate in any reaction. But once we make it into multiple blocks, multiple nanoparticles, so then obviously the surface area will increase. Once the surface area increase, that means more number of atoms will participate in any reaction, so that the efficiency will enhance for any type of application. Okay, so that's why here in second statement you can see this ratio plays a critical role in determining the physical properties and chemical properties at nano level. Okay, so the reason is at bulk stage less number of atoms will participate in reaction. In nano at nano scale, at nano size, more number of atoms are available to participate in reaction. Okay, so if you third point, as particles get smaller, their surface area relative to volume increases significantly, leading to altered reactivity and other properties. So that's what we discussed, right? So once the particle size is smaller, getting smaller from bulk to micro, bulk to nano, then what will happen? Obviously the surface area relative to volume increase. Okay, so that's why obviously the reactivity will increase. Once the reactivity increased mean obviously the properties will change. Okay, so at the nanoscale, atoms at the surface dominate over the interior. Okay, at the nanoscale, listen carefully, listen, read this one and listen carefully. At the nanoscale, atoms at surface dominate over the interior, impacting properties like melting point and chemical reactivity. That's what we have discussed, right? So at the bulk stage, most of the atoms are inside the bulk material, so which doesn't have any chance to participate in any chemical reaction. But the part once the material comes down to nanoscale, so that means, so when you make into multiple small pieces, so in just like nanoparticles, so then we have more surface area, so that more atoms come to the surface, so that it will participate in any chemical reaction. So that is the beauty of this nanoscale size. Okay, so this concept explains why nanomaterials often show superior catalytic, optical, and electronic behaviors. So this is the reason. This is the process of increasing surface to volume ratio. Okay. So once you enhance the surface area, then all these properties, all these behaviors will change. Okay. So understanding surface to volume ratio lays the foundation for innovations in energy storage, sensing, and environmental remediation. We have discussed, right, in our previous class. So in our previous class, we have discussed the applications of nanotechnology or applications of nanomaterials in various fields like medicine, electronics, right, in energy, in environmental field, right? So likewise, so we need to understand how this surface to volume ratio changes changes the properties of all these materials at nano level. Okay, so this is very important, right? Here you can see how we can what is this, can you guess what is it? Is it a top down approach or bottom up approach? Hmm? For example, if you go from left to right, like this, so this is top down approach. If you take large chunks and you make it into small chunks and make it into powder, so that is top down approach. If you take small particles, no, no. If you take atomic level arrangement and you then make up to this particles, that is bottom up approach. Okay, this slide gives you the information of top down approach. We take large chunks, it's a bulk material, and then it is a, you can call it this is a macro, this is micro, and this is nano. Okay, so this, so now tell me, so out of these three states, which state has more surface to volume ratio? which has more surface area? Obviously, the powder. For example, if you take a block, so the block can be it's very it can occupy a very small space, okay, small space. But if you make it into powder, the same block, the same material, but we make it into powder, but we can spread in a room, right? We can spread it into a room. So that means it can cover more surface area. More surface area means more surface atoms will participate in any reaction. Okay, so that is the importance of surface to volume ratio, so that you can understand how the surface area of this cube, how the surface area of this small cube, how will be the surface area of this powder. Obviously, the powder has more surface to volume ratio. Okay, right. Then how can we understand mathematically this surface to volume ratio? How can we understand? For example, see this. To understand the relationship between surface area, volume, and surface to volume ratio of spheres with different radii. Okay, for example, if you consider a circular sphere, sorry, a spherical sphere. Okay, if you imagine a sphere, for example, so look here, measure the radius of each sphere using the tools provided. So what is the surface area formula? 4 pi r square. What is the volume formula? 4 third pi r cube for each sphere. Okay, and if you divide surface area with volume, you can get surface to volume ratio. Okay, for example, here we will consider two spheres. One is sphere 1 have small radius and sphere 2 has larger radius. Okay, sphere 1 smaller radius, sphere 2 larger radius. So if you compare these, if you consider these two spheres with different radii, so then find out what is the, you can measure first initially radius, and then you will find out, you can measure with the formula 4 pi r square surface area. Okay, and also you can find volume, and also you can find surface to volume ratio. So if you find the surface to volume ratio of small sphere and larger sphere, so that you can understand, so which will get more? So definitely the small one. Okay, so right here you can see this, how this higher surface to volume ratio will play a role in changing the properties, whether it is physical properties or chemical properties. How the surface area to volume ratio directly involve or influence the properties. Okay, so see here, for example, if you see this graph, if you see this graph, you can see, so this is a large molecule, okay, large particle, you can say large particle. So then the size is reduced, then the size is reduced, then size is reduced. So this is the bigger particle, you can consider it as a macro molecule or macro particle. Okay, macro sized particle. So then we are decreasing the size. Okay, this we are decreasing the size. Obviously what will happen, see this one, this graph, so it indicates the melting point. Okay, it indicates the melting point. So once, see this one, this is the bigger particle macro, so this is the melting point, so it is around 1300, right? So once we are decreasing the size of the particle, decreasing the size of particle, so what is happening? It's directly proportional. So as the size reduced, the melting point also reduced coming down. Okay, so that means as the particle is decreasing, that means as the particle size falls from macro to nano, obviously the melting point is gradually decreasing like this. Okay, decreasing like this. Okay, right. Okay, we will see some important points related to physical and chemical properties which was influenced by higher surface to volume ratio. Okay, so high surface to volume ratio means more atoms or molecules are exposed at the surface, significantly impacting reactivity. That's what I have discussed earlier also. Okay, so more surface area to volume means more atoms or more molecules are exposed at the surface. Okay, significantly impacting reactivity. So once more atoms participate in any reaction, so that means the reactivity will improve. Once the reactivity improves, that means the efficiency of the reaction will increase. So whatever any of the reactions will significantly increase. For example, if you take catalysis catalysis is enhanced due to increased reactive sites leading to improved efficiency. Okay, leading to improved efficiency. Okay, at the nanoscale, properties like melting point can drastically reduce due to increased surface energy. So that's what about this figure, right? So this graph represents, indicates, what is it indicating? Hmm? So the particle size, as the particle size decreases, so the melting point decrease. What is the reason? Reason is more number of atoms will participate at higher surface area. Okay, so at nanoscale, properties like melting point can drastically reduce due to increased surface energy. Okay, right. Then next point, optical properties can change due to quantum confinement effects from small dimensions. Okay, just like chemical properties and physical properties, optical properties also change due to quantum confinement. What is quantum confinement? I will explain in few minutes. Okay, then high surface to volume ratio can also lead to faster oxidation or degradation of nanomaterials. Okay, so as the surface to volume ratio increase, so it will faster the redox reactions. So whatever once the redox reactions increase, then obviously the catalytic properties will enhance, so that we can, so this one is related to the we previously discussed, right, in environmental applications. So we have discussed that these nanomaterials are very useful to treat water pollutants and also air pollutants. Okay, water pollutants and air pollutants. Okay, porous materials and nanocomposites leverage high surface to volume ratio for energy and environmental applications. Okay, so if you see here the nanoparticles, so everything will matter: shape, okay, material, that means composition, and size, surface, everything matters. So everything will influence the final efficiency. Okay, everything will change. Okay, so understanding these implications is critical for tailoring materials for specific functions. Okay, so all these properties will change the surface to volume ratio. Okay, so some morphology, some shape will have higher surface area, some shape have higher surface area. Okay, so size matters, shape matters, and material, so what type of material it is, whether it is zinc oxide or ti wood or SN wood. So okay, so this material also, some materials will have porous structure. So porous structure will have will offer higher surface area to volume ratio. Okay, so finally we need to understand the effect of surface to volume ratio. We need to understand the importance of higher surface area. Okay, so lower surface area means less number of atoms will participate in reaction. High surface area means higher number of atoms, more number of atoms will participate in the reaction, so which finally affects the end application. Okay, okay, surface to volume ratio in catalysis. Now we will see this surface to volume ratio, how it affects different properties. Okay, so in this slide we will discuss about this surface to volume ratio effect in catalysis. Okay, see, if you see this image, so it is a nanocomposite. So these are metal nanoparticles, and these metal nanoparticles are wrapped within this graphene layers. Okay, so you can see the graphene layers. So these graphene layers are wrapped the metal nanoparticles. Okay, you can see the clear nanoparticles and also the layers you can see. So these are all graphene layers. Okay, graphene layers. So that means it is a nanocomposite with metal nanoparticles, that is zero dimensional, and the graphene layers, that is two dimensional. So it is a 0D and 2D combination nanocomposite. Okay, right. So catalysts benefit immensely from high surface to volume ratio, offering more active sites for reactions, more active sites for reactions. So we already discussed, right? So if surface area to volume ratio is more, obviously more number of atoms at the surface, that means more active sites for reactions. Okay, more active sites for reactions, more atoms are available, more atoms are available, more atoms are available at the surface. Okay, nano catalysts outperform bulk catalysts due to increased surface atom availability. So that's what we have discussed, right? If you take a bulk catalyst, less number of atoms available at the surface, so the participation is very less. But if you take any nano material, nano catalyst, the surface area is more, right? So once the surface area is more, obviously more surface atoms available, more surface atoms available means, so that means more active sites, more surface area, more surface energy, right? So that's why, so S by V influences selectivity and activation energy of catalytic process. See, for this catalysis demands or requires more active sites, more active atoms, more surface energy. Okay, so that's why, so to have more energy, more surface energy, we need more surface area. So if you see this picture, this graphene has large surface area because it is a 2D material, right? Because of its 2D material, it has more surface area, it has more surface area. So because of this more surface area, it provides more number of atoms at the surface, and thereby it has more surface energy. Okay, more surface energy. So because of this more surface energy, obviously the reactivity will high, and the efficiency of any application related to this composite will increase. Okay, so this surface to volume ratio can be tuned by controlling nanoparticle shape and dispersion. This is very important. So we can control the size and shape of particles through the preparation methods, right? So we have discussed bottom-up approach, right? So in bottom-up approach, we can by changing the reaction time, or by changing the selected precursors, or by changing the method, we can change the shape and size of the nanoparticles. Okay, so surface to volume ratio can be controlled by nanoparticle shape and dispersion. Okay, right. So then, in photocatalysis, high surface to volume improves photon absorption and electron hole separation. So why this surface area to volume ratio is very crucial for photocatalysis is, so when the material has high surface to volume ratio, obviously, so more number of atoms available at the surface to capture the light. Okay, to capture the light. So just like a person um, standing on the roof to catch balls. Okay, if many people are at the surface, so the people can catch a ball. Okay, so just like that, so if there are more atoms on the surface, so these surface atoms can capture the sunlight. If less number of atoms, so less capture of light energy. Okay, so that's why in photocatalysis, if you have high surface to volume ratio, that means high, more number of atoms at the surface, so the absorption will be very high. Okay, so if a material absorbs more number of more sunlight, so that the efficiency will increase by the process. For example, if you take a solar cell, Okay, solar cell. If you coat a material with high surface area, so that material can capture more sunlight, so that it can convert more electricity, right? So it can convert more electricity. Okay, so likewise in photocatalysis also, if it takes more absorption, so that more electron hole pairs can be generated. Okay, more electron holes pair can be generated, so that more redox reactions, so that is more efficient. Okay, so for in this particular case, photocatalysis, it requires high surface to volume ratio. Okay, right. Again, one more point. Catalyst recyclability and stability are influenced by surface characteristics. Okay, so just like a battery charging and discharging, charging, discharging, charging, discharging number of times for many cycles, so a catalyst should have this cycling ability. Okay, this cycling ability will be influenced by the surface area. Okay, if the material has more surface to volume ratio, what will happen? It can have, there is a chance for more stability, right? So more stability, so more stability and recyclability. Okay, so and also innovations in electrocatalysis for fuel cells and water splitting rely on surface to volume optimization. Okay, for fuel cell technology, water splitting means hydrogen generation. Okay, hydrogen generation. So in this process also, be in material science, so whatever the end application, it might be solar energy or electrochemical energy. Okay, so everything requires, every application requires nanomaterials, and these nanomaterials should have higher surface to volume ratio for any application. Okay, for any application, the nanomaterials or the nanocomposites requires higher surface to volume ratio. Okay, right. See this slide. So another field. So what is it? Energy storage devices. What are the energy storage devices? Hmm? Guess what are the energy storage devices? Supercapacitors, batteries. Okay, so these are energy storage devices. Okay, fuel cells, like that. Okay, so here in high, so how this surface to volume ratio impacts energy storage device performance. Okay, energy storage device performance. Okay, so high surface to volume ratio is a key parameter in the design of electrodes for supercapacitors and batteries. Okay, for supercapacitors and batteries. Okay, so for the most efficient electric vehicle, we need a good battery. A good battery means it should store more energy. Okay, so it should have high energy density, high power density. Okay, so right, so for this purpose, so we should make electrodes with the nanomaterials which should have more surface to volume ratio. Okay, more surface to volume ratio. Okay, and nanostructured materials provide large surface area, increasing electrochemical active sites. Okay, so what does it mean? Nanostructured materials. So different kinds of materials, right? Whether it is zero dimensional, one dimensional, two dimensional, three dimensional. So whatever the, these are all different nanostructured materials, right? So these different nanostructured materials should provide large surface area. So what will happen? Obviously, the electrochemical active sites will increase. Once the electrochemical active sites increase, so that it can store more energy. Okay, it can store more energy, okay, in batteries. Okay, so here you can see the different morphologies. It's a dots, right? Particles, zero dimensional particles. These are all one dimensional materials, right? Some wires or tubes like that. Okay, something like nanorods. Okay, these are all one dimensional material. Here you can see it's a two dimensional materials, something like amexine. Okay, amexine, graphene, GC3 and 4. Okay, so these are all two dimensional material. So it is a three dimensional material. So just like a ball, okay, just like a ball or flower, something like that. Okay, so it has three dimensional 3D nanostructures. Okay, 3D nanostructures. Okay, so these are all provide higher surface to volume ratio. Of course, one to one surface area will be different. Obviously, I will explain which nanostructures have higher surface area to surface to volume ratio. Okay. Uh, then here, see here, enhanced surface to volume ratio allows better interaction with electrolyte, improving rate capability and cycling stability. For any good battery, the stability is very important. Cycling stability is very important because so it's not one time charging and discharging, right? So we need to charge discharge many number of times. Okay, so that's how an electric vehicle runs. Okay, so as the number of charging and dischargings increase, usually what will happen, the volume will compress and expand, contrast expand. So but if it is this volume expansion contraction is more than a threshold limit, then obviously the life of battery will deteriorate. Okay, so that's why if the material has higher surface to volume ratio, it prevents this volume expansion much better. Okay, much better. So that's why, so the interaction, this enhanced surface to volume ratio allows better interaction with the electrolyte, and it improves the rate capability or and cycling stability. So the cycling stability will increase with the higher surface to volume ratio. Okay. Next, so I told you this is amexin. So amexin and transition metal oxides with high surface to volume ratio are studied for next generation batteries. At present, amexins are the hot topics. Amexin is a it's a two-dimensional material, so which are the layers stacked one to one. So stacked one to one. So these materials are hot topic in many fields, in particularly energy field. Okay, the future EV battery technologies focus on exploiting high surface to volume ratio for fast charging and higher capacity. So on the whole, we need high surface to volume ratio nanomaterials for the best batteries or for the best energy storage devices. So the simple thing you need to understand, we need nanomaterials, and that nanomaterial must have higher surface to volume ratio for better efficiency. Okay, next one, surface to volume ratio in photocatalysis and environmental remediation. So we already discussed that nanomaterials plays a major role in treatment in the air pollution and water pollution. Okay, for air pollution and water pollution, so nanomaterials plays a major role. Okay, right. So see this one, see this picture. So what kind of pollutants we can treat with photocatalysis? You see here, we can treat, we can use by using photocatalysis, we can we can utilize the water splitting process to generate hydrogen and oxygen. Okay, and also this process, by using this process, we can degrade the pollutants. Okay, we can degrade the pollutants like air pollutants or water pollutants. And also with this process, we can treat bacterial disinfection. Okay, bacterial disinfection. And by using this photocatalysis, and by using the catalysis, we can we can do this process, selective organic transformation. And also for CO2 reduction, okay, for CO2 reduction, we can use this process. That's why catalysis is very, it's one of the proven and well practiced process. Okay, right. We will see the some important points related to this photocatalysis. Okay, so this surface to volume ratio enhances photocatalytic activity by increasing light absorption and reactive sites. We already discussed that more surface area, more surface to volume ratio means, so we can increase more number of active sites, active atoms, and it so that it can capture more light. So more light means more absorption. Okay, and also photo generated charge carriers interact efficiently with target species due to larger exposure. Okay, we already discussed in previous slides that, so in redox, by using redox reactions, we can create photo-generated charge carriers, that is electron-hole pairs. So if a material absorbs more sunlight, more light, so that it can split or it can generate more photo-generated charge carriers, so that it can more these charge carriers can participate in many reactions. Okay, so that the efficiency of the process will increase. Okay, applications include degradation of dyes, pesticides, pharmaceuticals, and industrial waste. Okay, so we can treat air pollution, water pollution, right? So, for example, if you consider textile industry uses many colors, right? So many dyes. So all these dyes, so after their usage, so it's simply just convert into waste, right? So if that waste come to the canals, so it will make more pollution, right? Water pollution, right? So but these dyes we can treat with nanomaterials so that the impact can be reduced. It's just like dyes, pesticides, pharmaceuticals. So many chemical waste comes from industries, right? So to be it textile industry or pharma industry. Okay, so much waste into air and also into water. So we can treat up to some extent by using these nanomaterials, so that we can uh, reduce the damage. Okay, we can reduce the damage. Okay, so and also materials like TiO2, zinc oxide, amaxins benefit from nanostructuring to increase surface to volume ratio. Okay, and also if you see, so we already discussed, once we increase this surface to volume ratio, what will happen? So more sites will come. Okay, more active sites will create. So more active sites, nothing but faster reaction kinetics. Okay, faster reaction kinetics, so the reaction will be very faster. Okay, so that the impact will be more, the impact will be more. So environmental cleanup technologies now focus on nano photocatalyst with a tailored surface to volume ratio. I already told you. So to treat these environmental pollutions, we need nanomaterials. But even within the nanomaterial also, we can modify, we can alter. Okay, we can tune the shape and surfaces, so that to achieve higher surface to volume ratio. Okay, and the reaction efficiency depends on surface defect sites that increase with higher surface to volume. Okay, similarly high surface area to high surface to volume ratio also allows better dispersion in aqueous systems for wastewater treatment. For example, if you take a material with a macro size, so if you deposit in any water, so it cannot easily disperse throughout the water, right? But if you make that the same material to disperse into water, if it is a nanomaterial and it is if it has a higher surface to volume ratio, it can easily disperse throughout the material, throughout the water. Okay, so that the whatever the process we want, whatever the application we want, so obviously, so because of this higher dispersion, so the efficiency of the application will increase. Okay, so just like that. So nano composites combining high surface to volume ratio materials improve charge separation and visible light activity. We already discussed, right, in this photocatalysis. So two things are very important. One is light absorption, second one is redox reactions, so that is charge separation. Okay, right? So these two things are very important. So by using this higher surface to volume ratio, we can absorb more light, and more number of active sites will take that light or that energy and participate in activity. Okay, participate in the activity. So that's why surface to volume ratio is very crucial in the applications related to photocatalysis. Okay. So the next one is nanomedicine and drug delivery applications. In nanomedicine also, we need high surface to volume nanomaterials, which allows for efficient drug loading and release. Okay. So if you see this picture, you can understand the importance of drug delivery system with nanomaterials. Okay, drug delivery application of functional nanomaterials. See, you can see different carbon quantum dots. Okay, some polymeric materials, nanosheets, metal nanoparticles, like that. So these are all useful for the targeted drug delivery system in medical field. Okay, so we need nano carriers. Okay, nano carriers. So we see one image in last class, that nanobots. Okay, nanobots. So these nano robots or nanobots carry the medicine to the affected area, or to where we want to treat that particular part. Okay, so we need nano carriers with high surface to volume ratio, ensure better surface interaction with the biological membranes. Okay, so this surface to volume ratio material affects circulation time, targeting ability, and bioavailability of drugs. Okay, so in how much time we need to reach the targeted area. Okay, so the immediate reaction. Okay, faster response after taking the medicine. Okay, so that's also depends on the surface to volume ratio, and also it depends on enabling imaging, therapy, and sensing in a single platform. Okay, so usually before diagnosis some tests, we will take some medicine, right? So we will take some medicine. So likewise, to know the, for example, CT scans and MRI scans. So in some cases they will give a medicine before the diagnosis. Okay, so likewise, if we take that medicine within wrapped by the nanomaterial, so that it can open many functionalities, multifunctionality, so that we can take multiple diagnosis information. Okay, so likewise, increased surface area enables higher loading of hydrophilic and hydrophobic drugs. Okay, so we already seen, right, that in nature a lotus leaf has naturally hydrophobic material. So similarly, so we need some medicines, we need hydrophilic nature, and some we need hydrophobic drugs. Okay, so and also if we have higher surface to volume ratio material, then we can take more drug, more medicine. Okay, so sometimes we need more medicine to take. Okay, right? So in these cases also, this surface area, so higher surface area will be more advantageous. Okay, so and also nanoparticles with high surface to volume ratio exhibit superior penetration into tumors. Okay, so sometimes we need to just spray the medicine, and sometimes we need that medicine should go deeper into the tissues. Okay, deeper into the tissues. Okay, so in that case also these nanoparticles with high surface to volume ratio plays a major role. Okay, so that's what it means. Okay, so understanding surface to volume ratio is vital for safe and effective clinical translation of nanomedicines. So we need to understand the side effects, or how it affects, or how the efficiency improves. So we need to test everything. So before we use these nanomedicines for drug delivery systems. Okay. So then, so summary and future outlook. Okay. So what we have understood through this surface to volume ratio. Okay, so what we have understood, why we need to study surface to volume ratio, how it plays a major role in nanomaterials. Okay, so surface to volume ratio is a fundamental concept driving innovation across many disciplines. Okay, so we have seen that, so in any field or for any application, so we need nanomaterials, and also what else we need higher surface to volume ratio. So this higher surface to volume ratio is very important for all the applications. Okay, for all the applications. So understanding surface to volume ratio is crucial for designing functional nanomaterials and devices. Okay, to for any application, for any application so for any application we need nanomaterials with higher surface to volume ratio. And in what kind of applications we have discussed here, we have discussed in catalysis, in energy storage, in drug delivery, in environmental science, right? We have seen everything. Okay, in all most of the applications. So the next generation of technologies like quantum sensors, biointerfaces, nanorobots, relying on maximizing surface to volume ratio. So we need higher surface to volume ratio nanomaterials for different purposes, for different applications, whether it is quantum sensors, ultra sensitive sensors, bio interfaces, nanorobots. So okay, so future research will focus on sustainable materials with optimized surface to volume ratio for green technologies. Okay, what are green technologies? Electric vehicles, okay, solar energy, wind energy. Okay, so these are all green technologies, right? So water splitting, hydrogen. Okay, so all these depends on these materials, sustainable materials, smart materials. So we need to create smart materials with the required properties, and this required properties mostly depends on surface to volume ratio. Okay, so that's why surface to volume ratio is the primary and fundamental property which the prepared nanomaterial should have. Okay, so this is interdisciplinary collaboration, and it is a key to unlocking the full potential in surface to volume ratio in materials design. So whatever you think application, any potential application, any for any problem, our prime focus should be on higher surface to volume ratio. So that's why embracing the power of small offers transformative possibilities in science, health, and engineering. What is the power of small? This power of small is nothing but nano. Okay, this nanomaterials, this nanotechnology offers many possibilities in science, health, and engineering. Okay, so we will just remind all the topics we have discussed today. Okay, so what is the title? This one, surface to volume ratio. the power of small. Okay, right? So this is the introduction to surface to volume ratio. This is top down approach. Okay, top down approach. See, see the points, important points. If you see here, you see here, so this is the micro size macro size object, but once we the thickness is reducing, so the same material spread across like this. Okay, spread like this. That means, see, the surface area is here, just this much only. Okay, the surface area exposed, but see here, it's so much surface area. Okay, so much surface area, so that all the atoms here will participate in reaction, so that the efficiency will automatically enhance. Okay, so what is this method? Is it top down or bottom up? It is a top down approach, right? So macro to micro to nano. Okay, top down approach. Okay, so here you can see, if you take any radius, so 1 centimeter radius, 2 centimeter radius. So if you find out surface to volume ratio, so obviously the small radius will have higher surface to volume ratio. Okay, and also the physical and chemical properties, how it will change. See, what is this? What was the information you get from this? Okay, so as the particle size decreased, melting point decreased. So what it means? For example, if you take one material, so you are heating and it melts at 100 degrees. Okay, it melts at 100 degrees, but the same material, if you decrease the size, initially it is at, for example, let it be, it is around 500 nanometer. Okay, so 500 nanometer sized particles, melting point at 100 degrees centigrade. Okay, at 100 degrees centigrade. Then if you decrease the size from 500 nanometers to 100 nanometers. Okay, 500 nanometer to 100 nanometers. Initially the melting point is 100 degrees centigrade. So then as you decrease the size, the melting point also decreased from 100 to, let it be, 90 degrees centigrade or 85 degrees centigrade. Okay, so that's how, as the particle size reduced, as the particle size reduced, so melting point also comes down. So what if, for example, if melting point is at just 50 degrees centigrade, 50 degrees centigrade, so that means, so you can save more energy, so no need to give more too much heat or energy to reach 100 degrees centigrade to melt that material. Okay, so that's why this small size, this higher surface to volume ratio is very important. Okay, so how can we achieve higher surface to volume ratio? How can we achieve? By decreasing the size. By decreasing the size, we can achieve higher surface to volume ratio. Okay, this. So we have seen in different applications, right? In catalysis, surface to volume ratio plays a major role, right? It provides for better absorption, for better active sites, for better activity. Okay, see this energy storage devices. So for supercapacitors, for batteries, it is very essential, very essential. Higher we need higher surface to volume ratio. We need high surface area. Okay, so once it has high surface area, so that we can store more electrochemical energy. Okay, more electrochemical energy, more energy. Okay, so these are different types of nanomaterials, nanostructures: zero dimensional, one dimensional, two dimensional, three dimensional. So this is cycles. Okay, this is the um, testing, charge discharge testings. So these are all related to electrochemical studies. Okay, so this is charging, this is discharging. Okay, at different c rates: zero point 0.1 c rate, zero point 0.5 c rate, 1 c rate. Okay, so these are different c rates. Okay, at different conditions. And also in photocatalysis. Okay, in any, for to treat air pollutants, to treat water pollutants, just like textiles, textile dyes, textile waste, and also pharmaceutical waste. Okay, so these wastes make water with heavy pollutants, right? So very dangerous pollutants. So to treat all these materials, we can use this process, photocatalysis. Okay, so in this photocatalysis we need these nanomaterials with different nanostructures. Okay, different nanostructures we need high surface to volume ratio. So in this way we need higher surface to volume ratio for these applications. Okay, see this, see the image. So we need high surface to volume ratio nanomaterials for the drug delivery without side effects. Hmm? And also uh, for superior penetration into tissues, we need high surface to volume ratio nanomaterials. Okay, so right, see here the wastewater how it looks like. See, and after treatment, right? So if you treat it, so what will happen? See here, this is okay. So finally we can have clean water. You can see this one, this is nanobots, right? So previously we have discussed these nanobots will be useful for drug delivery in medical systems. Okay, so this is about surface to volume ratio. So in next class we will discuss about quantum confinement and optical properties. So how this quantum confinement, how will be the band gap changes with respect for macro-sized nanomaterial, macro-sized materials and nanomaterial. How quantum confinement plays a role in deciding the properties of nanomaterial, how it influences the optical properties. Okay, so band gap, optical properties, and display technologies. How these are interlinked, how these nanomaterials or this quantum confinement affects the end application. Okay, so we will discuss in next class about quantum confinement effect and optical properties of nanomaterials. Okay, so thank you very much. Uh, if you like this information, please share with your friends, like, comment, and share this video with your students and friends. See you next time. Thank you so much. Hello everyone. Welcome to the lectures on nanotechnology series. This is our third lecture. So in this session, we will discuss about quantum confinement. We already discussed about the introduction to nanotechnology, particularly introduction to nanoscale. So, what is the importance of nanoscale? We have discussed in our previous lectures. In this lecture, we will discuss about quantum confinement. Okay, quantum confinement. We already discussed in our previous classes that there are two main reasons for the beauty of nanotechnology or nanoscale. So, what are those? The first one is surface to volume ratio, and the second one is quantum confinement. Surface to volume ratio is very essential to be high for nanomaterials for various applications. We have discussed the importance of surface area to volume ratio in different applications in different fields, in medical fields, in material science, in electronics. Okay, so we have seen the importance of surface to volume ratio in many applications. So likewise, in today's lecture, we will discuss about quantum confinement. What is quantum confinement? How it brings changes when it comes to nanoscale. We will discuss all these things in this lecture. Right. So we are all aware of the types of materials we have. Okay. So everyone is aware that we have three types of materials. Okay. So three types of materials, usually insulators, semiconductors, and conductors. Okay. So in all these materials, so one thing we can commonly notice is the conduction band and valence band and band gap. Okay, so how do these band gaps form? How can we define a band gap? Okay, so in the concept of quantum confinement, we will explain about the formation of energy levels. Okay, formation of energy levels. How, see, the energy band is nothing but the cluster of energy levels. Okay, cluster of energy levels. The cluster of energy levels is nothing but a band. Okay, a band. For example, if you see here, first we will discuss about this, how these energy levels form. So our prime focus is on nanomaterials, right? So but before we focus on nanomaterials, we need to understand how the energy levels formed, how the energy levels will be in bulk materials, right? So how we are making nanomaterials? So we are making nanomaterials in two ways, right? One is top down approach, second one is bottom up approach. So in top down approach, what we are doing, so we are taking a bulk material and then we are make it into pieces, and then further grinding, then we are getting nanomaterials. That means we are making nanomaterial from bulk material, right? So from macro size to micro size to nano size. So this is the order we are following, right? So the energy bands in materials, if you see, so here we have three types of materials, right? So insulators, semiconductors, and conductors. Three types of materials. So if you see in insulators, so the green band you can see here, so it is a filled band. It is a filled band. So we have three types of materials: conductors, semiconductors, and insulators, right? Conductors, semiconductors, and insulators. Yeah. So here you can see insulators, right? Insulator, semiconductors, conductors, right? Conductors. So in this insulators, this is the filled band in every material. So this is the valence band and conduction band. So the gap between valence band and conduction band can be known as band gap. So similarly, you can see, so this is the conduction band in insulators, conduction band in semiconductors, and conduction band in conductors. Okay. So as we said earlier, so band gap is nothing but the energy gap between valence band and conduction band. So here the band gap is very high in case of insulators, and it is moderate in semiconductors, and it is very less, the band gap is very less in conductors. Okay, conductors. So how can this differentiate comes into picture? So we can explain based on the energy levels. Okay, based on the energy levels. So one thing we have to remember that the band gap is very high in insulators, and it is moderate in semiconductors, and it is very less in conductors. So what are the examples for conductors? You can see here the examples for conductor: gold, silver, copper, iron, aluminum. So these are all metals, right? So metals. So in these, so band gap is very less, almost zero. Okay, very less, you can say that it is very less. So because of this property, all these are very good conductors of electricity, very good conductors of electricity. So if you consider semiconductor, so what are the best examples for semiconductors? Silicon, germanium, selenium, gallium, arsenide. So these are all examples for semiconductors. So likewise for insulators, you can see here glass, rubber, oil, plastic, diamond. So these are all insulators. These are all bad conductors of electricity. Conductors are good conductors of electricity, right? So I already told you that how a band can be formed. So a band is nothing but a cluster of energy levels. Cluster of energy levels. See for here you can see continuous energy bands. In bulk materials, energy levels form bands. So this is important. Energy levels form bands. Okay, whether it is valence band or conduction band. So any band is nothing but it can be it formed due to the energy levels. Okay, so energy levels form bands. So in semiconductors you can find narrow band gap. Okay, in semiconductors you can find narrow band gap. So because of this narrow band gap, you can, if you supply a minimum energy or a small energy, so that the electron can easily jump from valence band to conduction band. In insulators, you can say that it is wide band gap, large band gap. Okay, so in metals, conduction band overlaps with valence band. So what is the advantage of having less band gap or moderate band gap or large band gap? Okay, so for example, if you take conductors, so what is the advantage? So because of this less band gap, so even if you supply minimum of energy to the electrons in in valence bands, so the electrons can easily jumped. Okay, because it is already almost merged, right? So valence band and conduction band are merged, so the electrons can easily pass from, or the electron can easily travels from valence band to conduction band. Okay, so in case of semiconductors, if you give a minimum energy to jump from valence band to conduction band, it can easily jump because it has narrow band gap, it has narrow band gap. But in case of insulators, so you need to supply more energy, you need to supply more energy, so that mostly the electrons cannot jump from valence band to conduction band. Okay, if you apply more energy, then only it is possible. So that is the fundamental concept of formation of bands. Okay, formation of bands and band gap. Okay, right. So now we come to the our main topic, quantum confinement. Okay, quantum confinement. Here you can see it is a valence band. Okay, so this is a valence band and this is conduction band. Okay, so in our previous class we have discussed about bulk materials. Okay, bulk materials, what are bulk materials, and okay, so what are macro size, micro size, and what is nano size. Okay, so we have seen the distinct difference between bulk materials and nano materials. So we will explain bulk materials, nano materials in terms of energy bands, in terms of energy levels, in terms of energy band. Okay, right, right. So here you can see this is the this is a bulk material and this nano particle. Okay, nano particle and then atomic level. Okay, so macro size to atomic size. If you see in bulk materials, the valence band and conduction bands, the formation of energy levels is very close, almost continuous energy levels, continuous energy levels. For example, if you if you take yes, if you take a book, if you take a book, you can see, so all the papers are stacked with each other, all the papers are stacked with each other, so almost continuous. Okay, continuous bands. Okay, continuous bands. Right. So for example, if you see this one, so all the pages are stacked with each other. Okay, all the pages are stacked with each other. So that means all it is a continuous band. Okay, continuous band. So in this valence band and also conduction band, so the energy levels are very close to each other, very close to each other. So it can form a band. Okay, it is a band, it's a continuous band. So okay, but when this situation comes to nanoparticle, nanomaterials, how can we define nanomaterials? How can we define nanomaterials? Any one of the dimension, any one of the dimension must be less than 100 nanometer, whether it is length or breadth or height. Any one of the three dimensions must be less than 100 nanometers. Then only we can say that it is a nanomaterial. So in case of such nanomaterials, how will be the energy bands? How is the energy bands? For example, if you here you can see in bulk materials, so it is a continuous. See, there is no gap. There is no gap in this band, so it's a continuous band. But in case of nanomaterials, what is happening? The energy levels are not continuous. See, the energy levels are not continuous. Then what it is? It is discrete energy levels. Okay, discrete energy levels. For example, if you see here, energy quantization is a fundamental concept in material science, especially at nanoscale. Nanomaterials exhibit significantly different electronic properties due to quantum confinement. So what is the application of this quantum confinement? So because of this quantum confinement, the energy levels are discrete. It's not a continuous energy levels. Because of this discrete energy levels, the band gap was significantly changed. The band gap was significantly changed. Okay, so we already know, we are very aware of classical mechanics and quantum mechanics. So where do we apply classical mechanics? Where do we apply classical mechanics? At larger objects, right? At larger objects, at macro size objects, only we can apply classical mechanics, Newtonian mechanics, right? But our discussion is at atomic level, at nano level. So at this stage, so quantum mechanics plays a vital role. Okay, quantum mechanics comes into picture, right? So quantum mechanics rules, quantum mechanics principles plays a big role to understand this nanoscience and nanotechnology. Okay, so because of this quantum confinement, we can see band gap in a different picture. Okay, in different picture, see here. So wave particle duality, we are all aware of it, right? So electrons exhibit both particle nature and wave nature. How can we understand this? See, for example, we are all aware that the energy, the electrons can be dual nature. Okay, both particle nature and wave nature. Okay, so by using photoelectric effect, you can understand the particle nature, right? So similarly, by observing the interference diffraction, you can understand the wave nature. Okay, so right. So at the nanoscale, quantum mechanics become more relevant. So that's what I told you, right? So at the nanoscale, quantum mechanics becomes more relevant. At atomic level, at a nano level, quantum mechanics plays a major role. But where the Newtonian mechanics, classical mechanics applied to larger objects, right? Larger objects, Newton's laws, right? Everything. Okay, so simply quantum confinement. What is the meaning of confinement? Confinement means restriction. Okay, restriction, right? So it restricts or it constrains the electron to bound within a within a region. Okay, within a region. Okay, so that's why it forms discrete energy levels. That's why it forms discrete energy levels. Because of this quantum confinement, because of this restrictions for electron movement, these discrete energy levels can be formed. Okay, the discrete energy levels can be formed. So simply we can understand that energy band is nothing but the cluster of energy levels, okay. Right. So how this band gap will be in nanomaterials, right? So as we understood that because of quantum confinement, so the energy levels will be in discrete form in nano size. Okay, in nano size. So the size dependent energy gap in nanomaterials. For example, if you see here, you can see here, so different size nanoparticles, right? So this is a bulk material. This is a bulk material. So this is valence band, conduction band. Okay. So because of bulk material, you can see the complete dark color. Why? Because it indicates the continuous energy band. It indicates continuous energy band. So once you come into nano level, so then you can see the and all the energy levels are discrete, discontinuous, right? It's not continuous, right? So and also you can see the band gap. So what is happening to band gap? So once the size is reducing, so bulk to nano, so 8 through 6 nanometer, 4 nanometer, 2 nanometer. See what is happening to the band gap? So band gap is increasing while reducing the size of the particle. So this graph also you can see here, it is 16 nanometers, 14, 12, 10, 8, 6 nanometer. So you can see on the y-axis band gap energy, right? So what is happening? So as the particle size, you can from right to left, as the particle size is reducing, the band gap is increasing. The band gap is increasing. So this is because of quantum confinement effect. This is because quantum confinement effect. So the band gap is majorly heavily dependent on quantum confinement. Okay, so one thing you must understood and you should remind it forever is, as the particle size decreased, band gap is increasing. So that means band gap is depend on the size of the particles, you can see here. So energy gap shift, smaller nanoparticle provides larger band gap. larger larger particles provides narrow band gap. Okay, narrow band gap. So and also we can tune the band gap, right? We can tune the, how can we tune the band gap? by tuning the size of nanoparticles. If you tune the size of, how can we tune the size of nanoparticle? I already told you. So we have different approaches to prepare nanomaterials. We have different approaches to prepare nanomaterials. We have top-down approach, bottom-up approach, right? In top-down approach, we have ball milling. So and also in many methods, okay, many methods. In top-down, in bottom-up approach, you have sol gel synthesis, combustion synthesis, right? Hydrothermal synthesis. So different kinds of preparation methods are available. So by changing the reaction time, by changing the pressure, by changing the temperature, right? By changing the duration of the experiment time. So we can change the size of the nanoparticles. Okay, we can change the size of nanoparticles. We can change the morphology of nanoparticles by changing the, by tuning the size and shape. We can tune the band gap of materials. We can tune band gap of materials. See, for different applications, for different purposes, we need a suitable band gap materials. We need suitable band gap materials. Depends on the application, our requirement of material with such, with suitable band gaps is required. Okay, so that's why band gap depends on size, and size can be tuned by experimental procedures, different experimental procedures. So we can change the, we can modify the band gaps by changing the experimental conditions with different approaches. Okay, so what is blue shift and what is red shift? So blue shift is nothing but emission wavelength decreases as quantum dot size decreases. Okay, as the quantum dot size decreases, the emission wavelength decreases. So red shift also. So I'll show you how this shift will happen. Okay, so simply, so all the properties can be tunable. So that is the beauty in this technology. We can tune, we can modify, we can alter the properties. We can alter the chemical properties. We can alter physical properties. We can alter electronic properties, right? So by changing the all these properties, we can we can enhance the application efficiency. Okay, we can improve the efficiency. We can increase the efficiency, right? So by controlling size, the material's energy gap and optical properties can be tailored. Can be tailored. That means can be changed, can be tuned, can be changed, right? So we'll see how this quantum confinement affects the surface energy. Surface energy. Okay, we will see quantum confinement effect and also surface effects. So here you can see from the previous picture. So this is a bulk material, right? This is a bulk material. Because of bulk material, all the energy levels are continuous. So you can see the thick, completely colored. So because of this bulk semiconductor, so the energy gap is, see the energy gap. So here you can see, so these are all under nano size. Let us assume it is a nano size. You can see here nano crystal semiconductors. Okay, nano crystal semiconductors. So here you can see the size is reducing. So the particle size is reducing, decreasing nano crystal size. So what's happening while decreasing nano crystal size? See the band gap is increasing. Band gap is increasing. Okay, band gap is increasing. If you go to atomic level, even it is still higher. Okay, still higher. So how these effects can be studied? You can see here, when particle size approaches the exciton Bohr radius, quantum confinement occurs. Okay, so when we can see this quantum confinement effect, at what stage, at what size this quantum confinement comes into picture? See here, when particle size approaches the exciton Bohr radius, quantum confinement occurs. What is Bohr radius? What is Bohr radius? You can see what is Bohr radius. See, the exciton Bohr radius is nothing but the average distance, the average distance between electron and hole, the average distance between electron and hole in an exciton. Okay, in an exciton. Okay, so this is a pair, electron hole pair. The average distance between electron and hole. So the average distance is nothing but Bohr radius. Okay, Bohr radius. So when the particle size approaches that much small size, then we can observe this quantum confinement effect. Okay, the quantum confinement effect, this is very very important. So we cannot see quantum confinement effect at micro level, micro size. We cannot see quantum confinement effect at macro size because the size is very large, very large. So when only the particle size approaches to excite on Bohr radius only, then only we can see this quantum confinement effect. So it observed only at such small size nanoparticles. Okay, at such small size nanoparticles. So quantum confinement alters electronic energy levels, affecting optical and electronic properties. The quantum confinement effect majorly alters optical and electronic properties. Why why So once this, because of this quantum confinement effect, what is majorly changing? What is majorly changing? Because of this quantum confinement effect, the energy levels, the band gap is altering. Okay, the band gap is altering. This this energy levels, the cluster of energy levels is this band, energy band, right? So this energy band. So because of this quantum confinement effect, band gap is altering. Once band gap is changed, obviously it affects primarily electrical and optical properties. Why electrical properties? If band gap is less, the electrons can easily pass from valence band to conduction band. So that is nothing but conductivity. So all the electronic properties depends on movement of electrons, right? Movement of electron. How the electron can move, how electron can jump from valence band to conduction band, right? So it depends, the electronic properties and optical properties heavily depends on band gap, and this band gap can be altered can by quantum confinement effect. Okay, quantum confinement effect, that's why quantum confinement effect alters majorly electrical and optical properties. So nanoparticles exhibit size-dependent band gaps. Smaller particles have wider band gaps. That's what we have discussed, right? So nanoparticles exhibit size-dependent band gaps. If you change size, if you change shape, okay, so if you change particle size, it reflects in changing band gap. Once band gap changes, then optical properties will change, electrical properties will change. So that's why, so it is heavily dependent on size. So that's what nano science matters, right? So nano size matters only at such small size, right? At such small size. So nanoparticles exhibit size-dependent band gaps, right? Another thing, so we already discussed about the importance of surface to volume ratio. Okay, the increased surface to volume contributes to altered chemical potentials and enhanced reactivity. So once it comes to such very small size, then obviously it enhances the surface to volume ratio. Once surface to volume ratio increases, then active atoms or active participants will increase. Once active participants increase, obviously the reactivity will enhance and the final application will be improved. Okay, surface atoms experience different coordination leading to new physical behaviors. Okay, so because of this quantum confinement, because of this less band gaps, then the surface atoms will experience different coordination with other molecules. Okay, so which leads to different physical properties. Quantum dots are a classic example where quantum and surface effects intersect. Okay, so surface effects and quantum effects, that's what we are studying in this slide, right? So both will come into picture at quantum level. Okay, at quantum level. So these phenomena are exploited in optoelectronics, biosensing, and photovoltaics. So these are the applications. So optoelectronics, biosensors applications, and photovoltaic. Photovoltaic is nothing but solar cells, right? So this quantum confinement, to understanding quantum confinement is very very important, just like surface to volume ratio. So to understand nanoscience, to understand the reasons for the different behavior of materials at nanoscale, we need to understand two things. So one is surface to volume ratio, and the second one is quantum confinement. Now you understood what is quantum confinement, right? So quantum confinement means restriction of electrons to a certain region, okay, to a certain region, okay. So we'll go further. Right. Surface energy and reactivity. So, how this quantum confinement brings the changes in band gap, and how this band gap changes the properties, we will discuss here. So, here also you can see the same thing. So, this is a larger particles, okay, larger particles, yes, larger particles, then small nanoparticles, then nanoclusters, then single atoms, okay. So you can see the size order also, size order. So it is in 100 nanometers, right? 100 nanometer. So this is 2 to 5 nanometers range, 2 to 5 nanometers range. So this is nano clusters. This is nano clusters. Then single atoms, it is in the order of 0.1 nanometer. 0.1 nanometer. So nano clusters 0.1 to 1 nanometer. Small nanoparticles 2 to 5 nanometer. Large particles, it is around 100 nanometers. So above 100 nanometers, we can say that it is a, it's not a nanomaterial. It's not a nanomaterial. So it is something like micro size particles, right? In micro size particles or bulk particles. So in bulk particles, what is happening in bulk particles? The valence band and the conduction band, it is a continuous band, right? It is a continuous band. But when it comes to nanoparticles, discrete energy levels, right? Discrete energy levels. And also the band gap will increase. The band gap will increase when come to small nanoparticles, right? So surface atoms possess unsatisfied bonds leading to higher surface energy, okay. So because of, at this stage it has higher surface energy. We can say that for bulk, in case of bulk materials, in case of bulk materials, surface energy is less. Can you guess why surface energy is less? It is related to surface area to volume ratio. So which material have higher surface to volume ratio? Bulk materials or nanomaterials? Obviously nanomaterials, right? So bulk materials, the available surface is less, right? The available surface is less, okay. So at bulk stage, the surface to volume ratio is less. So because of less surface to volume ratio, obviously the surface energy will be less. So that's why very less number of atoms will participate in reaction in case of bulk materials. In case of bulk materials, but in nanomaterials, what is happening? So obviously, because of the small particle size, so surface to volume ratio is enhancing, increasing. So because of higher surface to volume ratio, so this has higher surface energy, higher surface energy. So if a material has more surface energy, obviously its participation will be high in any reaction, in any reaction, right? So that's what it, let's say, surface atoms leading to higher surface energy in case of nano sized particles, okay. So this high surface energy makes nanoparticles more reactive and prone to aggregation. Aggregation means clustering, okay, clustering. So because of this high surface energy, the nanoparticles are more reactive, more reactive. We need more atoms, we need more particles to participate in reaction. So if more atoms are reactive, then we will get the advantage. We will get the advantage of all the atoms. For example, in bulk material, all the particles, all the molecules are uh, inside that material. So they are not participating. They are not on the surface to participate. So they are all useless. So no use, right? So once the particle to the surface, comes onto the surface, then only it has a chance to participate in reaction, right? So that's why we need we need all the atoms at the surface. Simply we can say that we need all the atoms at the surface so that all the atoms can participate in reaction. How can we bring all the atoms to the surface? Just by increasing the size of just by increasing surface area. By increasing surface area, how can we make more surface area? By decreasing the size, by decreasing the size of particles. That's why, because of these things, makes nanomaterials or nanotechnology is more prominent. Because of this kind of potential advantages, so it has that kind of possibilities, right? Possibilities. Okay, so we need to understand the meaning. We need to understand the science, the reason. Okay, so increased reactivity, enhance catalytic and chemical behavior of nanomaterials. We already discussed this point, right? So see, it's everything is interlinked. Everything is interlinked. So we are discussing at the very fundamental level, very fundamental, at very basic things. So we are discussing about the origins. Okay, origin for the change of properties. Okay, origin for change the chemical properties. Origin for change physical properties. Origin for change electrical properties. Once you know to play this modification, once you understand how can we alter energy levels, how can we alter band gap, how can we alter particle size. So if you understand all these things, so you can play so that you can modify as per your requirement. Okay, you can as per your requirement based on application. For example, somebody need more conductive materials, somebody need more chemically stable materials, right? Somebody needs more surface area materials, some application. Okay, so different applications demands different properties. Different applications demand different chemical properties, different physical properties, different chemical properties, different electrical properties. So based on your requirement, based on the application demands, we need to select materials, we need to modify materials. See, all the properties can be tuned, all the properties can be tuned. So if you know how to tune to reach your demanded properties, then it will be very easy, so that you can have whatever you ideas you have. So you can implement, you can try to achieve that idea. Okay, you can try to achieve that area. So that's what my intention is. You need to understand the very fundamental things. Okay, so that is at atomic level. Okay, at atomic level. So we can modify the band gap, we can modify the properties. Okay, so surface to volume ratio plays a major role in surface dependent process like adsorption and catalysis. Okay, so this is related to surface to volume ratio. And also we can change and also we can change. How can we, just now we discussed about altering the properties, modifying the properties, tuning the band gap. How can we do that? How can we modify surface energy? How can we modify, how can we enhance the reactivity? How can we improve the physical chemical properties or physical properties? See here. So tailoring surface energy via doping, coatings, or functionalization is widely practiced. By using these processes, there are many other processes also. By doping, we can change the band gap. By making composite or by making functionalization, so we can alter the properties. There are several methods to alter the properties. There are several methods to change the band gap, to tune the properties. Okay, to tune the properties. Okay, so surface defects and strain also influence reactivity at the nano scale. Okay, high surface to volume ratio enables development of highly efficient nanocatalysts and adsorbents. So higher surface to volume ratio leads to high surface energy. High surface energy. So these properties will decide the properties, chemical properties and physical properties and electrical properties and all things. Okay, so it will reflect in the efficiency of final output. Okay, final output. So the surface energy can be decided by this quantum confinement. Okay, so everything is interlinked. High surface to volume ratio, quantum confinement, surface energy, reactivity, right? So everything is interlinked, heavily dependent on one another, and these are all can be tunable. These are all can be altered. How can we alter? By the preparation process, preparing methods, by using different approaches. So every experimental method has its own advantages. So we will explain all in further lectures about different experimental processes. Okay, different experimental process. Then thermal, mechanical, and optical properties. So we have seen previously also surface to volume ratio, how it impacts thermal properties, optical properties, and electrical properties, like right. So likewise, here also we can discuss about the impact of quantum confinement, the impact of quantum confinement on thermal properties, mechanical properties, and optical properties. Okay, we will discuss some of the points. Nanomaterials with high surface to volume ratio exhibit improved thermal conductivity or insulation depending on structure. Okay, so we know that. So high surface to volume ratio will improve the conductivity. Okay, so mechanical strength can increase due to fewer internal defects and grain boundaries. What it means? For example, if we prepare a material and if it has some defects, some problems, some defects, some flaws, then it will affect the final output, right? Final efficiency. It affects the final application. Okay, so it may not reach as per our uh, our our efficiency percentage. Okay, so that's why, so we need to prepare material without flaws, without defects. So we must prepare a material which must meet all the requirements of the final output, final application. Okay, so for that, so mechanical strength is one of the major properties in related to mechanics. Okay, so how can we improve mechanical strength? How can we improve mechanical strength? So in our previous classes we have discussed this point, that we can, by using nanomaterials, by using nanomaterials we can make lightweight materials, yet it has more strength. Okay, more strength. We can prepare lightweight and strengthy materials. Okay, so how can we improve that mechanical strength? See, by taking care in experimental conditions. Okay, so we can make such kind of materials. We can, for example, if you take a carbon nanotubes, single wall carbon nanotubes, or multi wall CNT carbon nanotubes, so they provide higher mechanical strength. Okay, without internal defects and grain boundaries. Okay, so and also optical properties. Optical properties shift due to quantum size effects and increased surface interaction. We already discussed it, right? So we can tune the band gap, we can alter the band gap, we can increase the band gap or we can decrease the band gap by changing the size of nanoparticle. Okay, by changing the size of nanoparticles. In this way, we can change optical properties. Okay, we can change optical properties. And also within nano size, if you change the minimum size, some 8 nanometers to 6 nanometer to 4 nanometer to 2 nanometer, even in that case also the optical properties will change, not from bulk to micro to nano. Even within nano also, for 10 nanometers, 5 nanometers. If you take 5 nanometer particle and 10 nanometer particle, the band gap will change, right? Excuse me. So, so optical properties shift due to quantum size effects and increased surface interaction. High surface to volume impacts reflectivity, transparency, and color in nanoscale materials. Okay. So because of this quantum confinement and high surface to volume ratio, so even the change of size is small, 5 nanometer, 10 nanometer, 8 nanometer, 2 nanometer, like that, the color will change. The color will change. The absorption capacity will change. Okay, the absorption will change. The transparency will change. Okay, so all the properties, particularly optical properties, will change. The transparency, so if you want more transparency, you need to choose some particular size nanomaterial. You need less transparency, you need to choose particular size nanomaterial. You need high transparency, because for example, if you take solar cells, if you take glass doors, okay, glass doors, so how much light you want to abstract, how much percentage. For example, in previous class we have discussed, right? So we can coat with some nanomaterial, it can reflect UV back into the air. Okay, back into the air. So that's how we can filter out. Okay, we can filter out. So these properties can be altered by this size of nanoparticles and quantum confinement effect. See here, light scattering increases, influencing applications in coatings and sensors. So just like I told you, so in sensing applications and also in coating applications, so this quantum confinement, this size will affect more. Okay, so a lot of effects can be placed. So light scattering increases, influencing applications in coatings and sensors. Surface plasmon resonance arises in metallic nanostructures due to enhanced surface to volume ratio. For example, if you consider metal nanoparticles, for example, copper nanoparticles, silver nanoparticles, gold nanoparticles. So these metallic nanoparticles will show a behavior which is called surface plasmon resonance, SPR. We can say that it is SPR, surface plasmon resonance. So only these metallic nature nanoparticles only shows this type of surface plasmon resonance heavily. Okay, so because of this surface plasmon resonance, it can capture it can capture more sunlight. Okay, so it can heavily absorption. Okay, heavy absorption. So how can we improve that SPR? How can we improve surface plasmon resonance? Because of enhanced surface to volume ratio. For example, if you take 100 nanometer gold nanoparticles, 100 nanometer gold nanoparticles, 10 nanometer gold nanoparticles, so what will happen? Obviously, what will happen? This 10 nanometer gold nanoparticle will have higher surface to volume ratio, and also because of quantum confinement effect, the band gap is higher, so it can absorb, it has more surface area, right? So it has higher surface energy, so more gold atoms can participate in reaction, right? It can capture more sunlight, more reactivity, finally more efficient. Okay, more efficient. Okay, So these properties are critical in electronics, photonics, and composite materials. So all these properties, surface plasma and resonance and light scattering properties, optical properties, mechanical strength. So these are all can be influenced by quantum confinement, right? So how can we, what is the summary of this lecture? How can, what is quantum confinement? What this quantum confinement brings basic changes, what kind of basic changes? So quantum confinement bring changes all properties, mechanical properties, thermal properties, melting point, electrical properties, magnetic properties, catalytic properties, diffusivity, right, optical properties. So most of the properties, because quantum confinement is the reason, surface to volume ratio is the reason for the change in material properties when you compare from bulk to nano. Okay, bulk to nano. So that's why to it is very essential to understand the science of quantum confinement. Okay, so here are some of the key takeaways, summary of this lecture. Surface to volume ratio is a key driver for novel phenomena at the nanoscale. This is very important. These two things, surface to volume ratio, quantum confinement, will come into picture only at nanoscale. Okay, applications range from clean energy to smart medicine and environmental remediation. So we already discussed the applications of nanotechnology, applications of nanomaterials in various fields, in smart materials, in energy related things, in environmental, so in many fields, right? So high surface to volume ratio enhances performance, sensitivity, and efficiency across technologies. Future materials will be engineered for tunable surface to volume ratio and multifunctionality. So as we said earlier, so these two things, these nanomaterials bring changes in many fields, be it medicine, be it energy, be it environment, whatever it is, right? So it can influence, it can bring changes in many sectors, okay, in many fields. So interdisciplinary approaches are essential for innovation using surface to volume ratio concepts. Challenges remain in large scale synthesis. Yeah, still there is, it's not everything ready and everything available, everything reached and achieved. No. So still we are facing many challenges because preparation of nanomaterials at large scale, still it is a big challenge. Okay, so we can make nanomaterials, efficient nanomaterials with high efficiency in application. We can achieve in laboratory, but to scale it up to industry level, to a commercial level, so it is still a challenge because so when you make a material at small scale, so it can be it will be it is easy to control the temperature. It is easy to control the pressure, right? So that we can achieve the desirable particle size. We can achieve the desirable morphology. But when you plan to make it bigger, when you plan to large scale synthesis in terms of uh, kgs, right, in terms of, so usually in laboratories we will prepare in just mg level or sometimes gram level, but when you go to kgs, so in that much higher scale production, so it bit complicated to replicate the same size, same morphology, same performance, same efficiency. Okay, so that's why still challenges existed in this area. Embracing nanoscale design offers transformative potential in science and industry. Okay, so it will bring many novel things, right? So the key takeaways: quantum confinement means in nanomaterials, electron motion is restricted due to small size. Small size, at nano size, electron motion is restricted. Electron motion is restricted. That is what we are calling it as quantum confinement. Okay, quantum confinement. So leading to quantized energy levels. Okay, but in macro it is a continuous energy levels. But when the material falls under nano scale, okay, nano size, so then the energy levels are quantized energy levels. As the material size decreases, energy gap increases, right? Energy gap increases. So effects of size: smaller size, larger band gap. The size dependent energy shift is a defining characteristic of nanomaterials, right? So nanomaterials, we will see the presentation of today's presentation one more time. Okay, see the pictures. Bulk bulk materials, nanomaterials, valence band, conduction band. In valence band, continuous band, that's why it is completely colored, right? So all the energy levels are stacked with each other, no space, right? So if you come to nano, you can see the discrete energy levels, quantized energy levels, right? So if you go to atomic level, single level, just one energy levels, right? See, we have three types of materials: conductors, semiconductors, insulators. Examples: how is the band gap? Band gap is very high in insulators, moderate in semiconductor, conductor almost zero, because almost valence band and conduction band merge with each other. Okay, see here, that's what we have discussed in the entire lecture, right? Bulk, energy gap. See, the size of the particle is reducing, band gap is increasing. See here, from right to left, 16, 14, 12, 10, 8, 6, particle size reducing, band gap increasing. Y-axis, band gap. Particle size decreasing, band gap increasing. Okay, here also you can see the same picture. You can see atomic level, atomic level to macro level. So above this level, above this size, we can call it as bulk. Atomic level to bulk. Okay. So these are the properties: thermal, mechanical, and optical properties. So every properties can be tuned. Every properties, mechanical properties, thermal properties, electrical properties, magnetic properties, optical properties can be tuned. How can we tune? Just by changing size, just by sizing and just by changing size of nanoparticle. Okay, size of nanoparticle. We can tune the size. We can tune quantum confinement effect. We can tune surface to volume ratio. We can tune surface energy. We can tune properties. We can tune properties. So by tuning the properties, it will affect the final application, final efficiency. For example, if it is a battery, it improves energy storage. It improves energy density, power density, cyclability, stability, right? So it will like this. So in case if it is a solar cell application, so the conversion ratio, solar light to electricity, the conversion ratio will improve, right? Will improve. For example, if it is a self-cleaning material, self-cleaning glass doors, and also in medicine, right? So drug carrying nanobots, right? Nanobots. So the material with high surface to volume ratio can easily disperse and completely disperse in a material, right? So depends on the application, we can tune all these properties. We can tune all these properties. Okay, so these are very basic and fundamental, very basic and fundamental. So this is about quantum confinement effect. So up to in these three lectures, we have discussed about what is nano size, nanoscale, right? So what is the difference between bulk materials and nanomaterials? How can we make nanomaterials? how can we make nanomaterial in top down approach and bottom up approach, right? So how can this nanotechnology or nanoscience comes into picture due to its small size? Okay, we have discussed all these things, right? We have discussed, and what are the two reasons for this existence of technology? So two reasons, based on two reasons we can explain everything, right? So one is higher surface to volume ratio, and second one is quantum confinement. So for nanomaterials, for nanomaterials, we need higher surface to volume ratio. We need higher surface to volume ratio. Okay. So and also this quantum confinement bring changes in band gap. Okay, which reflects in all the properties, particularly optical properties and electrical properties. Okay, so this is about quantum confinement. So if you like this content and information, please share this video. So like this video. So if you have any questions, you can comment. So I'll try to reply to all your comments. Thank you for watching this lecture.